afternoon, everyone. Hi, my name is Kerry Lynch. I'm the CEO of Power Nickel, and welcome home to our podcast today. And we'll be talking about our the title is basically Fleet Space Tech, launching Power Nickel's exploration to new heights. So we're looking forward to talking with our friends from Fleet. And today, representing Fleet was Bronwyn, Murphy, and Nick Smith. And obviously, from us, we'll have myself and Ken Williamson, our VP of Exploration. So I'm going to give a brief introduction on Power Nickel and sort of how we arrived at working with Fleet Space Technologies and their amazing new program called ambient noise tomography. And then we'll switch over to Fleet. They'll give a bit of a background on their company, what their objectives are and how they go about it, and how they're interfacing with us on NISC. And then we'll switch to Ken, and Ken will run us through how Power Nickel is using this great technology to advance our exploration program at NISC and what our go-forward plans are. And at the end, we'll wrap up with some questions. So without further ado, we'll give you a quick rundown on Power Nickel. So our current, the way we sort of see ourselves, we were positioning ourselves in the market as the best nickel investment on the planet. So we'll jump into the next slide. We're not going to tell you anything we don't believe is true, but it's always good to do your own due diligence. Where we're located in the world is important. We're located in Quebec. Quebec is arguably the best jurisdiction in the world for looking for critical minerals. Three primary reasons. Number one is they got tremendous infrastructure. We happen to be located off of Route North, right across the road from us is a Hydro-Quebec substation. Our workers drive to the site each day, and they drive home on this beautiful highway, 8 kilometers to Nemaska, where is a nice regional village. It's got a regional airport, and they stay in a really nice a lodge that's owned by the Cree, who are our Aboriginal partner. They basically the First Nations partner, and the Cree government is also resident in Nemaska. So they've become a ongoing partnership with Power Nickel, and they're one of the great things about Quebec is they've done an amazing job working with the First Nations on making them partners in mining projects, and that's just so important because community risk is a big part of mining, and in this case, the Cree. The James Bay Cree have in this neighborhood about 4 mines being either built or being built. So that's obviously fantastic. And then the final reason why Quebec is such a sensational location is, of course, the fiscal incentives there in Quebec and Canada are top tier, nothing like it in the world. So you get, such things as 2-for-1 exploration. So we've done several financings where their stock's been 25 cents and we've, raised money at 50 cents and some cases at 90 cents. So, it's been an amazing way to eliminate dilution for our shareholders and to get the exploration capital we need to advance the project towards, production. It's also phenomenal from a production standpoint. In the future, when we go to build this mine, we hope we'll be able to, look at, tax credits from the federal government of about 30%. And from the provincial government of Quebec, about 25%. So that's to equip and build a new mine. So that's just an amazing start that you can go in terms of expediting things forward. So that's why we love Quebec. Next slide. Yep. So when we say we're the best investment deal in the planet, we really have 2 things that we point to, because we don't want to sort of talk full of hot air. We like to deal with facts. So the first fact is we compare ourselves to other high-grade nickel sulfide plants projects around the world. These are projects that have 43101s but are not built. And then we look at, sort of the minerals that are covered, et cetera. And when you do a quick look at that, you'll see that we're the lowest valuation there. And now that we've reported the new 43101, all of a sudden our grade is really catching up. So you can see that on a sort of market cap per ton of resource, we're the cheapest by a lot. So we think that sort of presents a lot of upside for our investors to get into. And now we'll walk you through the exploration story in 1 second, but we'll switch to the next slide if we could. The other part of the story is that we're not going to be building just an ordinary nickel mine here where we make nickel concentrate. We're working right now on a feasibility study with our partner and investor, CVMR Inc. CVMR is a very large private organization. They're probably best well known, I would think, because they had made the nickel plate that makes the US $100 bill, which is a pretty interesting conversation. They also do the super colliders where they have these $10 million nickel tubes, and they make them. Their biggest customer is the U.S. Department of Defense, where they have 2 joint ventures. So they're obviously a very experienced group. I think they're probably, the top technical nickel producer in the world. And what's interesting about them and their approach is there's basically 3 ways to make nickel. You can smelt it, you can use hydrometallurgy, or there's chemical metal vapor process, and that's what they do. It's the lowest impact on the environment, and it leads to finished products. So we make powders, nano powders, wires, anodes, and precursors for the battery metal companies, and that leads to much higher revenue. They generate between 2.5 to 3 times revenue versus selling for conventional concentrate. So, we're going to find a lot more nickel and rich nickel PGMs, etc. And then we're going to basically produce it in a way that maximizes revenue. So that's why we think it's such a great investment opportunity. Now we're going to just walk you through how we arrived at working with Fleet. So we started off with a historical resource of 3.1 million tons. Next. And then, we basically needed to confirm that existed. So Ken Williamson, back when he was just consulting to us, came up with the plan to do that. And we hit on 7 of the 8 holes, and that's why we fell in love with Ken. So next slide. So then we basically started to reel off some tremendous exploration success, 40 meters in the center of the hole there of 1.6% nickel. Next slide. Followed that up with 10 meters of almost 3%. Followed that up with, I think, 16 meters of 1.6%. Followed that up with 15 meters of 1.5. Generally, we're hitting on probably 50-60% of our holes where we're getting good mineralization, like 1% or better. And this is now what it looks like in terms of like an ore body. And we've got some holes that are still pending that will come out. But we've made a lot of progress, and that's allowed us to obviously update our 43-101. This is what the ore body looks like now. And we just reported basically 7.2 million tons at about 1.13%, which was a little bit less than what we had hoped. But generally, that's a result of the metallurgy. For a concentrate, the metallurgy process is a little bit different. And so the grades there are not as high as we would have liked on the concentrate, because we lose a lot of the mineral stays in the ground. However, with CVMR going forward, if we go with the finished products approach, we expect that to bounce back up to 1.5. So that's exciting. So at the end, we ended up producing this, this result. Note that most of it's indicated. So when we were initially putting it together, we were sort of fairly cautious as we, expanded our resource and moved forward. But now that we've got these enhanced tools like ambient noise tomography, which we're going to get into in just one second, we're going to be able to, I think, grow the resource a lot more rapidly going forward. So how big can it be? Well, one of the things we have like a 45 square kilometer package, and the package sort of it's ultramafic in nature. It stretches out about 7+ kilometers going sort of, middle to northeast. And we stepped out almost to the end of it to Wildcat. And what did we hit there, Ken? The next slide. We hit an amazing.
I wouldn't into myself. Sorry about that, Terry. Wildcat was a little different. Rather than hitting really good grade in nickel, what was there was spectacular grades in PGEs. Over an ounce PGEs, over 7 meters plus, I think it was.
Yeah, I think it shows on the next slide, right? So. Yep. So maybe just show that. So that's what we hit, and then we sort of knew, wow, we had this, crazy, 5.5, 7 kilometer corridor that we're, looking at potentially, and we thought this is a very big animal that we're dealing with here at NISC, and then we started to sort of look around and say, okay, we've got the conventional tools that you absolutely must have, like downhole EM, airborne EM, IP, gravity, all those tools that and that's in every geologist and geophysicist pocket. But we were looking outside the book to sort of see what else is out there, and we had saw that Talon Metals, or we expect, had announced that they were using Fleet to do some exploration on their very fine deposit in Michigan, Minnesota border. And when I saw that announcement, I thought, well, I'd never heard of it. I thought I'd better check it out, So I, follow the peers that are doing well, and they were doing great. They're sort of like at the top of the charts in terms of the junior nickels. So I reached out to Fleet, and they I talked to them. They sent me some white papers. It made a lot of sense to me, but I'm not a scientist, so I'd be easily fooled. So I brought my scientific team in, Ken and the guys from 3D, from GeoVector, who have been doing an amazing job in executing our program and advising us every step of the way. And these are, Joe Campbell and Adam and Eric, and these are top tier professionals. And they were initially quite skeptical, I got to be honest. And I said to them, I said, guys, look, if you decide this is not for us, fine. But I'm spending the money. I want you to get educated. It's on my dime and our dime, Power Nickel's dime. And if you get educated and decide it's not for us, then we'll just walk away because you're the scientist. But after 2 or 3 sessions with Fleet, they became convinced that Fleet was the way to go. And we're super happy we did. So now's the timeline. I'm going to turn this over to Bronwyn, and Bronwyn's going to explain to us, with Nick's help, all about Fleet, and then we'll continue on with the show.
Great. Thank you so much, Terry. So a brief introduction. I am Bronwyn Murphy, a geologist and geological client manager with Fleet. So I worked really closely with the Power Nickel team over the last about 6 months on their project, taking it from the deployment stage through to the results and interpretations. And with me today, I have one of our senior geophysicists, Nick Smith. Nick was the geophysicist on this project, so knows the ins and outs of the velocity of responses, and he'll be walking us through the technology today as we move forward. So just a bit about Fleet. So Fleet Space Technologies is an exploration company, whether that be on Earth, Moon, and Mars. Our interest is pushing exploration to the extent, and the company was founded in 2015. We have 7 satellites in orbit, and we use those to collect data from our geodes, which Nick will touch on in a little bit. One of the things that I love about Fleet is we have a really diverse background of people who work here. We have over 30 nationalities, and that creates a really great atmosphere for working in a company that deploys our product all over the world, and then also we're going to space. So that's a wonderful thing about Fleet. And with the ambient noise tomography in our ExoSphere product, we have deployed over 180 surveys worldwide. And so with the product, we wanted to support mineral exploration. So we wanted to find a way that we could really contribute to the industry that is progressing into an age of environmental sustainability. Resources are getting deeper, harder to find, and we want to assist in that process and make sure that exploration is as efficient and economic as it can be, and also environmentally friendly. So that's our ExoSphere product. And in-house to support these exploration activities, we have over 150 years of geological and geophysical experience. We have over 6 geophysicists at the moment supporting these projects, and some geologists on our team as well. So this group is what is the backbone of the exploration program and helps us to come up with the great models that we produce, and also the interpretations of those data sets directly with our clients as well. So what I'm going to do is I'm going to hand it over to Nick, who is our ExoSphere and ambient noise tomography expert, to take us through what that looks like.
Thanks, Bron. So yeah, in a nutshell, ExoSphere is the ambient noise based offering which Fleet offers to its customers. In a nutshell, what ambient noise tomography is, it's a 3D scalable data set. We optimize to image velocity structure down to about 2.5 kilometers, and we have a vertically integrated business model for this offering. So we also manufacture the sensors, and we also manufacture and maintain a satellite constellation which the sensors will talk to. So really versatile, scalable method, which is extremely vertically integrated across our businesses. And one of the biggest things is it allows us to do geophysical surveying with very little environmental impact. That's important for a variety of reasons. So yeah, next is basically, in a nutshell, this is the way that the surveys work. So we engage with our customers. The ambient noise tomography in itself it's a non-linear geophysical inverse problem. So we typically start these surveys with a desktop study. So that you can see number one there, we ask our customers to give us some orientating geological and geophysical data, which we can then understand the project. The second point is we ship our geodes out to the customer. They will deploy those in on their projects, and they can, by having this near real-time data view, we can optimize those surveys on the fly and redeploy once we know the required amount of data has been collected for that particular survey. And our ExoSphere platform allows the customers to see that data coming in real time and see those results extremely rapidly. So a bit of a nutshell again about why we're interested in using ambient noise. So ambient noise tomography, it's a passive geophysical method. So our sources are not generated by us. They're purely natural field fluctuations. So essentially we pick up those natural field vibrations. We extract surface waves from those, and we can use that to image the Earth in a way which is extremely analogous to an X-ray in medical imaging. So all these things come together to essentially form an extremely versatile and scalable 3D data set, which is, it adds a huge amount of value, not only in itself, but also to interpretations, bigger picture interpretations, and bringing in and gluing all geophysical and geological data sets together for a more kind of coherent and informed geophysical and geological models at the end of the day.
Great, thanks, Nick. And we will get to a point in the presentation today where we have a Q&A session. So if there are specific questions about the technology or what the results come out looking like, please feel free to ask those questions as we move forward. So with Fleet, we have completed over 180 surveys worldwide. We have clients all around the world, and we're working on various deposit types. We work in copper porphyries, IOCGs, nickel deposits. We're looking at uranium unconformity deposits. We're looking for a water exploration program as well. So it's a really diverse data sets that we're working with. Power Nickels was one of those really great projects that we've just completed. So they did their field season just June, July, August this year. So here is the map and location of the Nisk deposit and Wildcat exploration site that we deployed the geodes during this past summer field season in Canada. So on the map here, you can see that we've done a couple of different survey designs. We've done the tighter space arrays, so these are all geode locations. And those are what we call the infill surveys. So those are the higher resolutions when we're focusing on kind of specific geological areas and when we're trying to get a better idea of the geology. And then we do what we're calling regional exploration sites, where we do slightly larger spacing of the geodes. It allows us to cover more area, but slightly lower resolution. So you can see the 5 surveys that we covered over at the Nisk deposit, and then the Nisk main, just for reference, sits along these between kind of this green and blue section here. And this orange to the northeast, that's our Wildcat exploration zone. So that was one of the kind of step out surveys that we did to try and connect the geology between Nisk, which had a lot of background geological information, to an area where there was not a lot of drilling or other geological activity. So with the Nisk area, we did the infill spacing and the regional. So we did about 150 and then 400 meter spacing for the geode. So that's how far apart each of those nodes are. And then with that spacing, that ties into the resolution. So for the infills, we were looking at about a 30 meter resolution, and we got down to 300 meters depth. For that regional grid, we're a little bit less resolution at 80 meters, but here we were really looking to depth of the deposits to see what was happening even further down than their deepest drill hole. So we went down to about 875 meters and covered quite a bit of area over that property. Wildcat was exploration, so we used a bit of a wider spacing to get a broad brush idea of the geology there. So we had about a 50-meter resolution and 500-meter depth over that property. So the ExoSphere results. So when we the satellites are transmitting the data, that comes through to the ExoSphere platform, and our geophysicists jump in and they start QCing the data and building the 3D velocity model. So these are the exports of the 3D velocity model for NISC at the top and Wildcat towards the bottom. And with the mineralization and controlling features of NISC, what we're chasing here is these ultramafic packages. And how those come through, those are really high velocity responses in our 3D models. So right away, you can see that we're picking up these kind of isolated zones of these ultramafics along the NISC deposit, and just labeled here is where the NISC main is. And also in Wildcat, you still get a very similar velocity response where we have ultramafics present. And it's interesting, so along strike of these ultramafics, we have a change in the velocity to a low and medium velocity, which does correlate to some of the metasediments and amphibolites that we see in the deposits, and that's confirmed with drilling. And the velocity response is very distinct on NISC main, and the profiles and what we're going to get into with the live demo. Ken's going to walk us through what that looks like in the 3D space, because with the velocity models, that's one of the benefits. We can see structures at depth, we can see bulk changes in lithology, depth of cover, all those sort of features that you can't pick up from other geophysical methods you see in the ambient noise tomography surveys. So that's really the benefit of the product, is being able to see these big transitions and big scale features at different deposit types. And so to give you kind of another idea of how to visualize the data and what we're looking for, so these are a little bit more of a three-dimensional view of those ultramafic packages. So we see they're trending roughly along the same strike, but we're starting to see some diversity where we have segmentation of these ultramafics. We have pretty significant dips in the velocity, and this cross section here is centralized around NISC main, and Ken will get into a little bit more of what that interpretation is and how it compares to their other geological data sets. So you can see a long trend. We definitely have this lower velocity response along these ultramafics, and then some interesting features segmenting these units as you move to the northeast. The last slide here is a generalized geological map of the NISC main lithologies, and in red is the main sulfide mineralization. So we will get into that in a little bit more detail, but you can see right away that the ANT surveys are really picking up nicely those trends from where we have the metasediments into the ultramafics, and that's the big takeaway from this project, because the whole system is focused on these ultramafics, and that's showing up really, really nicely in the ANT data. So I know everyone's quite eager to get into the live demo and also the question and ask period. So I'm going to hand it over to Ken to take us through that process.
Thank you, Bronwyn. Everyone's eager except me. I'm nervous now. That's the risk of doing the live show. So without further ado, you should see my screen, and I apologize, I will just use PowerPoint as is. Just to jump back a little bit on the regional geology component of the project, and I'll try to lead you guys to understand how important that ANT tomography or ANT survey has been for us. So now, if we look at the regional geology, what we'll see first and foremost is the NISC main, as well as most of our targets like Wildcat target to the northeast, NISC west also, which is to the west. All of them lenses seems to be related somehow to a regional structure, which marks the contact between rocks to the north and a sedimentary package to the south there. So when I first got into the project, was the striking thing to me, was, okay, it's likely not a structural controlled deposit, but definitely there is a structural component that could happen after. And let's see how that plays with the interpretation of the main lens on its own. So now, having that picture in mind, what I'll do now is I'll jump directly to the Leapfrog project, which is a work in progress right now. So from there, with that regional geology in mind, one of the most the best tool that we have in terms of seeing through and seeing what the geology is definitely was mag data. So at the very start of the project, this is the type of data we had to play with. So it became very, very intriguing to me to realize that when we follow some of the mag features, like here, that's a diabase dike, all of a sudden the dike is changing orientation slightly, and that led me to clue in, well, perhaps there are regional secondary structures that are related to that major break that I shown earlier. So now, based on that, and based on all of the drill data we had at the time, and that we keep gathering as we speak, what I ended up doing is to construct a full-blown 3D model of the lithology and trying to highlight the structural component on that lithology model. So based on a combination of data and interpretation of such a mag map, what we can see from there is a little model that I created to cover the, well, as much as I could, the whole thing here. So that cube that we'll see now in 3D is meant to represent what the geology is all about. So as Bronwyn mentioned, the geology is predominantly showing us an ultramafic unit that is the key marker unit, both in terms of geophysical response in terms of mag, but also, as she mentioned earlier, in terms of velocity signature. So the model we came up with showed very nicely and clearly the geology we had in front of us. And then from there, we've explored the data a little bit further to end up with the geology or structural geology component of all this. Now I'm just trying to clean up my image by removing the surface data. So now we can see the full extent of the 3D model we've done. And throughout the data, if we were to look at this in a much more closer look, we would recognize in plan view, for say, we would recognize that the contacts between the ultramafic rocks and the rest are showing little variations in terms of direction. And that's the raw data being modeled as is. So now when we were to compare these strands that we recognized here as little, perhaps secondary structures cutting the deposit, it became really clear that if we use then a much higher resolution mag data set that we ran over the survey, that all of them features we could probably bridge with some of the breaks that we would see in the mag data. So that became really, really interesting. And from back to the drill hole data, exploring that data set in great, great detail, what we came up generating here is a series of little volumes that represent what I believe are dikes in the system. So I'm going to show them all on screen right now, just getting the model a little fainter. Sorry about the live thing there. So with all of them structures interpreted, it became pretty clear to me that them dikes, for instance, that are across the data set are representing definitely structures. So now, based on that, the problem we had is we had detail on the dips and strike of them structures and dike at that scale, but what was about the more regional scale? And that's when we heard about Fleet and the ANT survey. And when we realized that the survey itself could provide to us information at depth using those velocity contrasts to distinguish between, you know, rocks that are heavy versus rock that are less heavy, or showing a lower velocity contrast in that case, we decided to give it a shot and see what it would provide to us. So now, when we first loaded the data, I have to admit it was a little bit of a challenge to understand what we were looking at. And we, with the help of Bronwyn, explanation from the Fleet crew, finally understood how to actually play with the data in a very efficient way. So a little bit as what Bronwyn showed you or showed to us earlier, what I ended up doing is from the raw point set, or the interpreted point set that I received but imported as a raw point set in the system, it became possible to start exploring what that thing was showing us. So now one of the idea was to not show all of the velocity ranges that are displayed here on the right of the screen, but rather displaying them by skipping one. So you display number 1 and 3 and 5, etc., and that is enhancing quite a bit the view we can have through the data set. So if we look at that from a plan view, we see the entire data now. What we can do to explore that a tiny bit better would be, for instance, to only look at them velocity ranges one by one. So if we start with the lowest velocity ranges, that's nearer or closer to surface, by spinning this in 3D, we will recognize some bubbles, I guess, or some bulges that are dipping or sinking down in that data set. So right there, we could see that there was something to do with this. But that was not the end of it. So if we keep going, and I'm not going to do the entire exercise here, but if we were to keep going and look at some other velocity ranges, say at mid velocity range, then we would see little holes in the data set and things like that. So, and culminating with the very highest velocity ranges that sits at the bottom, and being able to convince ourselves that anywhere between that transition across red and any other color was the contact between the ultramafics to the south versus any other types of rocks to the north. So with that, and that is a very, very similar view to what we were looking with Bronwyn a little earlier. But from there, what has become very, very interesting was to compare the results of that survey with the actual geological interpretation we have, both on the lithology side, but also on the structural side of things. So what I'm going to do is I'll just go back to the initial view, showing a few of them ranges here. And from a plan view, we'll just simply cut here a section from, say, the western side of the deposit, and we'll look our way towards. I just need to make sure that I'm looking at this the right direction here. Okay, and then we'll make our way towards the northeast. And again,
yeah. So just for context, so Power Nickel hasn't done a ton of exploration work to the west, so it's right. So that we're just moving through towards the NISC main.
Let's start the other way.
Doesn't matter.
So we'll start from east and we'll make our way west. Makes more sense. Yeah. So I'll just keep a perspective view here so we can appreciate the 3D nature of the data set, not only on a section view, but we'll be able to see strikes a little bit within that slab. So from the west, and to help ourselves out here, what I'll do is I'll load up what the NISC main lens is looking at and where it's located actually in the system. So that's our main NISC zone, and then you see at the very far east, it seems to coincide fairly nicely with a drop here in the that velocity contrast between orange and red. So if we move our way towards the west more, and we do it a little faster, what we'll realize is at the core, or near the core of the deposit, definitely there is a break here in the velocity contrast, and we believe that this here marks the ultramafic unit. So right where we see such a break in the footwall of that contact would therefore be the ultramafic unit, and as the nickel sulfide lens is hosted by that ultramafic, it becomes straightforward targets for us, if it's not drilled, obviously. So we're still in the core of the deposit here, where we can still see that very sharp velocity contrast, and then all of a sudden we'll reach the end, or the western end of the known portion of the NISC main. So if we keep looking at what's happening here from one section to the other, that becomes really, really, really interesting, as we will see that contact here where the NISC main lens is centered at. We'll see that contact all of a sudden shifting a little bit further south and sinking down pretty much. So here's that contact and the really sharp switch in location that is happening between that one given section and the other. So the interpretation we now have is that there are those series of faults, subsidiary faults that I was related to earlier, that are likely part of that same northeast running structural corridor, are definitely impacting the deposit. Is that a bad news? No, not at all, because with the understanding we have now, having incorporated that 3D data set into our system, compared it with structural components and things like that, it just tells us where, well, we believe is the rest of the deposit, or so to speak, the offset portion of that deposit across them faults that we are now identifying quite easily using that data set here. So if we were to keep going our way west, then we'll see that that contact still is preserved, and then at one point may become faint or something, or even more pronounced, but no actual geological data in those areas, no drilling, no nothing. So obviously to us, it becomes prime target areas that we'll want to test. And not only that, it seems that the profile also shows the same kind of break or signature that we had seen. I'll just go back here. The same signature that we had seen for NISC main seems to not only repeat itself across fault, but it seems that we're also seeing other breaks like that that could lead to other pods as well, or definitely other targets as well. So to us, that became very, very a key data set that I've used quite a bit, actually. And I'm told by the fleet group that I'm probably one of their client that has used the most that data set.
You're the best user, Ken.
Well, for a very good reason, because it's super interesting. And what I ended up doing actually is building manually my own interpretation, I guess, of the data. And what I came up with is designing a series of interpreted lines, I guess, that I've built on sections. So if I show you guys a little bit what I've done here, is based on section view. I'll just recut a section here just to show you how I've proceeded. I've just basically designed rough polylines that are marking where I saw the transition between velocity contrast happening. So that would be for the first layer, and then I've done that for the other layers. So we can't really see now, but what I'll do is I'll explode the view again, and for temporarily I'll get rid of the point set here if I can locate it in my menu. So I'll just have it really, no, not even, I'll just close it off. So when we look at those polylines that I've made, there are some views, and when you rotate it in 3D, there are some views that definitely shows breaks in the data set. Like for instance, in here, where you have all of them blue lines pretty much lining up in those orientation here. Those are definitely the faults that I was referring to earlier. So those relatively low angle faults that are impacting the system. Sorry, sometimes we can't see it. So from them lines, what I ended up doing is to simplify our view a little bit more. I ended up creating them surfaces that are representing pretty much what the point set is telling us, like in a summary, if we can say it that way. So when we take time to evaluate and have a look at all of them surfaces together, we will definitely see them breaks happening. Some breaks seems to be cut by others. And I do believe that this is telling us a little bit more about the chronology of them structures. So another piece of very, very valuable information that we're learning from that data set as well. And from those surfaces, what I ended up doing actually to ease the pain at looking at the data, because the point set is sometimes very difficult to look at. What I ended up doing here is converting them surfaces or contact into volumes in between the different velocity ranges, thresholds that I've used. So if we were to look at the entire ant model that way, what we would see, and I'm just trying to relocate it in my list here. So what it would be looking like is something like this. So if we start from the bottom, we'd have a couple areas that the velocity is super high and super deep. So it's creating those two holes kind of in the system here. And then if we load the layer just above, so the velocity one notch lower, well, yeah. So then we start seeing a little bit more of the detail about the location of them ultramafic units. And the same thing's going to happen if we were to load up all of them layers one by one to finish with the top layer. So the advantage of dealing with the data set that way is that now we can cut section and actually have a look through the velocity model in a much more, I'm thinking, better visual way, much easier to see things in there. So what I'll do is I'll just get rid of all of them little faults, but I'll preserve where NISC main is on that image. And very fast, if we were to rebrowse again the same data, we would observe the same thing as I just described with that velocity contrast contact here, shifting at one point when we move to the west, shifting a little bit deeper. And if we are to do the same exercise, but then moving east again towards the end of that data set, what becomes really, really interesting is we won't lie, we're kind of losing the lens a little bit to the east there. But the thing is, again, we believe that it's a fault cutting across, moving the lens a little bit further east and deeper. And the ant profile is kind of suggesting that is happening when we look at where the location is of NISC main here, just right adjacent to that very sharp dipping velocity contrast. And then if we continue moving east, we'll see that is disappearing. But at one point further down the road, we do see a little bump down in here with a lot less resolution in that part of the survey. But from what we understand, it may mean that in here is the same velocity contrast break that we're looking for, the same signature, and that whole area became to us the ANT2 target area. So ANT number 2, that is to the east of that. So all in all, when we look at not this, because that we can't see nothing, but when we look at the overall story here, not only we've, I believe, understood very well what signature we are looking for, but definitely the ANT survey has allowed us to confirm literally the structural hypotheses that I had to start with. And we can see even in the main lens where there is little variations, and it's very subtle, but it coincides really, really nicely where we can see breaks in the ANT survey data. So that was comforting me quite a bit, to tell you the truth, because it seems to work really, really nicely with the interpretation, but it works nicely because the response seems to be very, very nice and great for us. That is very, very cool. So another view that we can have a look at there is a long view throughout the lens and see what are we learning from nickel distribution versus that ANT profile that we see here. So since the beginning, I've displayed the lens as a shape or a volume, one color only. So what I'm going to do is I'm going to replace that by the Ni% numerical model that we have. So just for the time being, I'm going to hide voluntarily the ANT profile and just focus a tiny bit here on that long view, which is showing distribution of nickel grade in percent. So pretty easy to recognize a couple of things in that slide. Well, if we look at the odd colors, we'll see a couple very high grade shoots that are sticking out from that long view. And then if we look at the cold colors, we'll see definitely some breaks, it seems, within the lens itself. So we interpret them blue areas, breaks, areas being faults that are impacting the fine scale location of the lens itself, and some other faults on the boundary of the known NISC main lens, some other faults being related to them breaks, and more major faults that we have in the system, leading to those offsets and generation of targets and things. So that being said, if we put back the ant profile on there, and I'll just minimize here the slice width to about 50 or even 20. 50 was better. So what we can see is where we had interpreted faults to happen, definitely there's a very sharp change in the profile in that long view, which is super interesting. And again, we will recognize the same thing happening to the northeast here with that shallower trending line here, which I believe represents the intersection lineation between that major fault that we have to the east leading to Ant2 on the other side. So in whichever view we look at this, it seems that we're confirming the primary hypotheses that we had. And from there, quite frankly, we've explored quite a bit the entire survey, but we're yet to complete the exercise. We've identified so far a bunch of targets that were the most obvious. We're yet to have a second look at that in a much more detailed way and identify other targets that are further away from NISC main still.
And could you show us a plan view of the Ant1 and Ant2 trends?
Sorry, what?
Could you show us a plan view of the Ant1 and Ant2 regions?
Yeah, absolutely. So let's get right now the plan view through the model, and I'll get back to the I can get back to the point set. But I think in here, just a random cut plan view here definitely shows those oblique breaks that we're referring to since the beginning here. So the Ant2 would then be following that break that we have to the east. So if you take the main lens and you break it or cut it and offset it in that location that the profiles indicated to us at depth, then that became prime target ant number 2. What is ant number 1? Well, ant number 1 is that trend that leads towards the wildcat target area way up northeast, about 5.5 kilometers away, which coincides realistically with that regional break that we've looked at earlier. So, and then if we explore to the west, then we'll recognize again potentially major breaks here that are slicing and dicing that still, and then therefore prime target areas to rediscover equivalents of the NISC main pod somewhere else along the property.
And we are moving at depth a little bit more in those ultramafics as we move west. So I think there's like a couple of drill holes that weren't quite deep enough as we were stepping west. And that applies for also, I think, 1 or 2 of the drill holes that were in the northeast as well. So one of the things that we were doing is pulling up some of those drill logs and saying, okay, well, where are they placed in relation to the ANT data? And if we had drilled a little bit deeper, what, would that have been our recommendation? So it's one of the things that Ken and I have been discussing a little bit, as well as the site team, the GeoVector team as well.
Absolutely. And what's really, really cool to do is once all of those exercises were done and discussions with you, Bronwyn, and the entire team, and when we, at one point, I guess we can say we finally understood what the heck we were looking at. Now was time to go back to the initial data set and compare, with what we had to play with before. So perhaps what we can do here is to show again some of the MAG data we had to play with, and have a little look, trying to understand what the heck is happening here. Oh, okay, I get it. Sorry. So when we compare the mag data we had on surface from before with the ant profile, it becomes really, really cool to observe a few things. So now I'll try to do that live. So bear with me a sec here. So what I'm going to do, one of the exercises we can do to compare things together is, what if we are convinced now that we've identified those breaks that are oblique to the mainland. So what if we are to look at them, say, along them? So we look on a long strike view here of them break. So on that view becomes very, very obvious that there is a sharp break there, and we can definitely see its dip. So now when we combine that to previously acquired data, and that's where I'm trying to see here the whole thing together, is you take a view and then you convince yourself, okay, I'm looking along strike a major fault seen by the ant survey. You realign camera, and then all of a sudden you start seeing the same kind of breaks happening in the other data sets, which is very, very nice to have, because it to me did confirm actually that the signature we were seeing from the ant data is something that is real. We can support it with other data, not only the drilling, but also mag data seems to show a response that is compatible with the ant survey and things like that. So very clearly becoming a complementary tools to all of the other tools that I knew of before. So it was really, really cool story for me, that thing. And to end up the whole story here, if I'm going back to more, hope that's the right one. So if we're going back more to the regional view, we've covered essentially that area here with great detail. We've ran a survey at Nisk, Wildcat area, sorry, to the northeast in here. And at this point, based on the very successful interpretation we had on that survey for Nisk, Maine, what I'm trying to do at this time is to redo the same thing with the Wildcat data set, such that we can better prepare ourselves for what's coming up next after Christmas, which will be drilling that thing as much as we can due to the very high grade in PGEs that we've discovered there. So, and after that, that rig being set up, the intent is to bring a second rig at site to actually and effectively drill all of them identified targets, starting from Ant 1, that is where my cursor is, along that trend leading to Wildcat, Ant number 2, which is, we believe, the equivalent of Nisk, Maine, but further east and a little deeper, and Ant number 3, which is the same thing, but on the west side in here, and Ant number 4, which is in that location way further west here, where the same signature has been observed when we compare that location to Nisk, Maine. So very cool tool that led us with a lot more confidence at designing them targets and better spending that money drilling those areas underground. So I think it covers it for me.
Okay, Ken, thanks so much for that. That's obviously a lot of intel for everyone to absorb. And you want to reduce risk of drilling, because drilling is expensive. That's your last resort. You got to do it. That's how you ultimately make discoveries. But you want to get as much of the brain work you can possibly done. And what we've found is that in my observation as just a business guy in terms of spending the capital, is that by getting this intel together, this operating system overarching above the downhole EM and the IP and the magnetics and all that, and pull it all together, you could really start to see, the layout of the possible growth of your deposit, and then we were able to get a lot of intel, and then obviously we expect to, apply it, in the winter program, starting, early in January and continue on until, break up in April, May, and we'll be adding a second rig, and who knows, so we expect to really step this up, and then ultimately, we didn't touch, we probably don't have time today to get into the deeper stuff, but I will make an observation that nickel, generally speaking, is not something you find at surface too often. It's generally a deeper metal. Like if you look at all the big discoveries like the, Raglan and Voisey's Bay, which are very close to home and for Canadians, it's basically there. It goes from 500 kilometers down to probably 2 kilometers. But Norilsk is a classic. It's literally the world's biggest and most valuable mine, and started as a surface deposit, close to surface deposit, and then over the years they discovered that wow, there was some amazing stuff available at depth. So that's the thing that we love about NISK, from an asymmetric investment perspective, is that we've got, this nugget of NISK main that's being very prolific. It looks like it's got legs and we can add to it. And looks like there may be these, Ant 1, 2, 3, and 4, all relatively near surface in geological terms, that offer us great opportunity to expand that. And then we also have the upside of potentially the depth thing, and that's ultimately what we'll be bringing back, fleet in for next summer's program to, obviously the good news is as we drill, we get more accurate data. It goes back into the ANT system, and they can iterate, and then it gets smarter. It's like it is AI, so it gets smarter with it. And then we've got, like, obviously the experts from their side, people like Nick and Bronwyn, who are working with us, not just with the Power Nickels of the world, but with many other clients, and learning all sorts of new enhanced approaches to how to analyze the data and how to make it work for us. So let's get to some questions from some of the audience here. I had one detailed question, which we may or may not be able to do, but I do want to bring it up here. Let's see here. Can you show lithiologies on a NAF track plot? I have no clue what that is, not being a geologist, but maybe Ken or Bronwyn, you guys know.
Ken, you're on mute.
Sorry, what type of map?
A NAF Drake plot. NAF-Drake
plot. I'm gonna have to be honest, and I'll Google that up.
Okay. So while you're looking at that, we'll ask some other stuff. That one of the questions was, does Fleet see this being a university course at some point? That this will be something that all geologists and geophysicists will need to learn. Has there been any conversations that way?
Yeah, it's definitely a tool that would be great to add to any explorationist toolkit. Nick, our geophysicist who's on the call, he actually has been running a course and to how to interpret the data for exploration companies. Nick, do you just kind of want to give us a brief about what that course looks like?
Yeah, sure. So it's just a little bit more of a deep dive in terms of the physics, I guess, behind the method. So there is, I guess, a level of understanding which is necessary in order to make the best use of the data sets. And if you look at, ambient noise tomography compared to, say, gravity or magnetics, what those other methods represent, and how do you actually invert those for physical properties, the ANT is quite a bit more complex. So yeah, the whole idea of the course is to build a little bit more intuition around what the data sets represent, what their strengths and weaknesses are, what the different methods that we employ during the processing are. Ultimately, we're trying to build intuition here, so the data sets are delivering the best value possible.
Yeah, fair enough. Question we had on just the chap who asked about the North Drake plot. suggests it's the velocity of P waves versus density. So I'm sure that sounds like a geophysical thing to me, but I'll throw that out. Nick, is that something that you're familiar with?
Yeah, so I don't have the plot or that information for NISC, the specific example, but yeah, I mean, that's P wave velocity maps to density with a more or less linear trends for common rock types. So example of common rock types, you know, we're looking at, you know, sedimentary rocks versus igneous rocks versus metamorphic rocks. That trend is useful to kind of, if we have drilling, for example, with a lot of density data measured on that, then it's useful to inform or to constrain velocity structure in our models, either be it a starting model for the inversion or more on an interpretation basis. It's also worth pointing out that trends, that mapping of density to velocity, it breaks down under certain circumstances, and one of those is when we have highly altered rocks, also when we have mineralized zones. So yeah, we utilize that trend in some parts of our interpretation process, but it's more of a guide. And also worth mentioning that the surface waves which we extract from the ambient noise, we model the actual shear wave velocity from that information. So shear wave velocity is different to the P wave velocity. It's slower, but again, it does map with a relatively constant ratio from VS to VP. So yeah, there's a couple of layers of information there. Summary is we can use that mapping of density to velocities as a guide for interpretation.
Okay, cool. So another question, what creates ambient noise in a very remote location, i.e. place with no roads or volcanoes or trains or twisters?
Yeah. So it depends on frequency. So high frequency, so above 5 hertz in this example, generated predominantly by human activities, and that's, you know, infrastructure, mines, towns, and these things can be, you know, around 50 kilometers away or up to 100 kilometers away. Say if you have a town which is generating noise around 5 hertz, above hertz, you really need sources which are quite close by. And at low frequencies, we generally don't have an issue with sources because the generating mechanisms are large scale atmospheric effects. We're talking about swells interacting with the shallowing of the depth of the water, the continental shelf, the margins of continents, and these waves, these sources generate low frequency signals, so below 2 hertz, and they propagate for many thousands of kilometers. So generally, we're readily able to acquire the low frequencies, and high frequencies, depends on the area of the project. But it's also worth mentioning that so the geode, which is the sensor which Fleet manufactures, is designed specifically for picking up these weak sources in the ambient noise wave field, and so it allows us to go to a little bit higher frequency and build up signal faster than, you know, other nodes which are commercially available.
Okay, so question. Terry mentioned that you had a roughly 50-60% success rate when drilling in terms of intersecting the mineralized zone. What percentage of the drilling was done before using the ANT application? And what percentage success do you expect to get now that you're using the ANT application? We drilled most of it before ANT, I would say. Just the last, maybe the last section, and probably in the fall we started to use it. But Ken, maybe you want to take that one?
Yeah, well, actually, we haven't tested really nothing using the ANT technology, except I would see the deeper part of the deposit right now, and a little bit to the east. But I guess we were interpreting the ANT survey and getting to a conclusion.
2203-036, we probably did because we sort of saw that it looked like it was okay when it initially looked like it. Our theory was it wasn't going to be good, and then when we saw the data, it sort of showed that no, that's probably going to be okay, and then we stepped out 300 meters and hit it. So that was one for sure.
Yeah, absolutely.
Yeah. The other stuff, we've got the data now. We're going much deeper, on certain trends on the core NISC main, and then we've identified this ANT1, ANT2, up to ANT4, and we have not done anything on those yet. But and there's still work for the team to do, over the holidays, from now until mid-January when we pick up again, is to just to again crunch all the data and look at it from a variety of different fronts, and then we'll start to test it. There's a question out there. What would you think will be your level of accuracy going forward? And I don't know. Do you is that something that you guys have? You've got. I think you said you read 150 or 180 surveys. I'm sure you generated, I don't know, 900 or 1,000 targets. I don't know if you've done any back testing on this to see what's the success ratio and stuff.
It depends on the property really, and what the results are coming through. We've definitely had clients drilling specifically on the areas of interest that the surveys have shown and Fleet have identified with really good success rate, but it is dependent on the project. So what ExoSphere and the ANT surveys is good at doing is mapping those bulk changes and those really interesting kind of larger scale features. And we're also considering the resolution as well of the data sets. So for the NISC deposit, where we had the infill survey, so we were dealing with about a 30-meter resolution. So when we're looking at features, we keep in mind that accuracy as well of those data sets. And as we get deeper into the model, the resolution does change a little with depth. But your trade-off is seeing those big scale features lower in the deposit types. So it's really dependent on the deposit, but we have had a really good success rate. I can't give you a specific number because not all the time it's fed back to Fleet, but the clients that we've worked with closely and have drilled a few of the targets based on the responses are very pleased with their process. Sorry, go ahead.
No, go ahead. Go ahead, Bronwyn.
I just wanted to tie that into one of the questions that popped up about using ExoSphere and the geodes on a purely exploration-based survey. That's definitely something that we do. We're currently working on a project in South Australia that the only geological data they have is a map from the 1970s. So other than that, we are going completely blind, and that survey is our deepest to date, so up to 3,000 meters depth. And we have a lot of other clients using it in a purely exploration sense, and the model does have really good velocity responses in all of those cases, and that's what we're looking for. So either changes in lithology or big structural features that cause changes in the velocity response, such as faults and folds, those still pick up really well. And we don't need constraining data to make a model, but it is helpful for the interpretation process and tying it back to what the field geologists have interpreted already. And that's one of the great things about working with the clients and that we have a designated team at Fleet, is that it's a collaboration process to analyze the data and work through the results, regardless of if it's a known deposit or not.
Obviously with NISC, we were fortunate. We had a bunch of drilling data, a bunch of the other data sources that we could look at. Is your sense that given that we run both a narrow and a wider survey, that are what we see as ANT 1, 2, and 3, and 4, they're unlikely to be mirages. They're in your view, if one is definitely a mirage and 10 is a ore body, how are you feeling about those targets?
Well, I think that's a me and Ken question, or Nick. Nick, go ahead.
I'll just jump in quickly. So surface waves, when we model these surface waves, really what we're looking for is for contrasts in bulk velocity structure. So in this example for NISC, we actually see that it's a perfect scenario for the method, because we see these offsets and these contrasts, lateral contrast between high and low velocities. So we're able to image how these packages are offset, and we're able to image the packages themselves. So it's more difficult when the contrasts are more subtle, or the features that we're looking for are quite small in proportion to the array station spacing. So I think to answer the question, in this case, we do see these contrasts in bulk velocity structure, and we also see a really coherent strike orientation of that response, which is not constrained at all by outside data. This is purely model data driven. So yeah, a lot of these features do build up our confidence in the models at the end of the day. So I think, yeah, to answer the question, they're probably not mirages. I won't give you 100% confirmation.
You mean you can't guarantee we're going to hit nothing but pay dirt? I mean, come on.
Well, I mean, in geophysics, all models are wrong, but some are useful, and I think that certainly applies in this case.
No, I appreciate that, and I think I don't think we all know that Mother Earth is a tricky rascal, and she never makes it easy on us, but it is an important new tool, and clearly we think it will enhance our odds dramatically. And the neat part about this is that, if we drill one of these structures and we don't hit, we're going to learn from it, and they'll be able to reiterate off that learning. I think that's the other important thing, is that, and it's like when people say, well, why don't you hit 100% of your holes? If people just haven't been around mining, whatever, they don't realize that you got to miss, otherwise you're not doing your job, because you're not pushing the envelope. So in order to really, you got to step out and miss. Otherwise, you're not going to find out where the constraints are for your ore body, or your deposit, or your mineralization. I don't want to get into any 43101 trouble. It's such as it is. But I mean, generally speaking, that's important, and it'll be the same thing with this tool, and that there'll be a series of targets that it'll identify, and as obviously they've done with us, and we think we'll be more successful with this than any other tool we could be using. And I'm sure we won't hit 100%, because nothing works 100% of the time, but we'll also learn from it. And then, maybe the next time we'll be able to get even more success. That's, would you agree, Nick, that that's sort of a good way to look at it philosophically?
Yeah, absolutely. And particularly, moving forward into next year, we're constantly looking at ways where we can deliver a result which has a lot more geological context. So at the moment we model data in terms of velocity structure, but really what we wanted to move towards is geological inference from the data sets. So that kind of, it's a lot closer to the geology. It's a lot more useful for validating exploration targets and hypotheses moving forward. So yeah, particularly, that's where we want to go. And I'd also mention that the addition of the velocity data, so the geometries and the velocity structure you get from that model, it works as an independent constraint on all your other geophysical data. So when you try to extract maximum value from your exploration data sets, it's really important to have data which constrains other data, so you can get a nice coherent, well-constrained geological model hopefully out at the end of the day. And that's kind of what ANT really provides at this point.
Yeah, I agree 100% on that. I had a question. Does ExoSphere share any similarities with the Typhoon technology that iPulse, backed by Robert Friedland, has developed?
I understand that Typhoon is a distributed IP system. So no, I would say that there's no similarity there in terms of the method, possibly in terms of some of the back end software there might be, but I'm not aware of any. Okay.
What is the resolution depth extent of the ANT survey?
Yeah, so for this one, for the infills, we were down about 300 meters, and for the regionals down to about 900 meters. But yeah, I mentioned before we have a survey going that's about 3 kilometers depth. So it's all dependent on the geode spacing, and that obviously impacts the depth and also the resolution. So with each client we work with, we set out the objectives and what you want to do, what the regional and local geology is, and what the target zones are, whether it's analyzing structural controls, or if you have certain mineralization that might cause a difference in velocity response. All of those features we take into consideration before designing a survey. And we have a team of experts that will design it to make sure that we hit exactly what you're looking for depth and resolution. And the way the geodes work is we can manipulate these surveys on the fly as well. So for deployment, we usually have a couple teams of 2 or 3. And those teams will deploy the geodes. It's a very easy process. So they're just put into the ground. I saw a question about whether we've done any Arctic Circle work, but we need that coupling of the geode to the ground surface to record that information. But the teams will take these geodes, whether it's on foot, or in Power Nickel's case, we did some helicopter work. We have a client who's using horses. So it is really diverse in that deployment process. But generally, you can deploy these geodes in a day or 2 days, depending on the field size and the spacing between the geodes. Once those geodes are in the ground, we make sure that there's satellite connectivity so that data can be transmitted right away, so that we can start collecting the data and have those models generated as soon as possible. So with Power Nickel's case, we did the 6 surveys over the field season. They had a team on site that was obviously doing the geological work on other projects, but also helping out with the deployment of the geodes during that project. So the way it works as far as the programs, the geodes are leased to the clients for a certain amount of time, 1 month to up to 6 months or more for some of our clients. And it's as many surveys as you can get done during that time. And then the data collection period is dependent on the signal that the geodes are collecting, as well as the data quality. So it's a big balance, but Fleet kind of guides you through that process the whole way. And you get models generated as that process continues. So instead of a 3-6 month turnaround with some traditional methods, we are turning around models in a couple of days from data collection. So it really can speed up your exploration process, for your projects.
So we're going to get one more question here, and then we'll just do a wrap up before we go. So one of the questions was, does ExoSphere add information that is simply not available by other means, or does it effectively just accelerate the time scale for collecting the data? I don't know who's best, Nick or Bronwyn, whoever.
Yeah, I can probably have a stab at that one. Yeah, so it does both basically. So clearly it accelerates the acquisition and delivery of results from the data sets, but critically is it goes back to what is the makeup of the ambient noise in a particular project area. So typically when we go into a new project and the first survey of that, we'll deploy a subset of the geodes, so maybe 5 geodes, say in a small array, and from that information or from that data set, we can determine the composition, frequency composition, and directionality of the wave fields. And then that information is critical. It's absolutely critical for designing subsequent surveys, which best adapt to the wave field conditions and deliver the best model. So I guess the analogy for this is an ultrasounds. So you have an ultrasound wand, and you have some detectors, and you have an imaging technique. And the idea is that you can move your ultrasound wand around to better image the target. And that is exactly what we try to do with ExoSphere, having that real-time information coming in. We can determine the wave composition, frequency, content, directionality, and then subsequently design arrays which are best suited. And again, just to reiterate, those high frequencies are really important for detailing our model, but they are also the hardest ones to pin down and understand. So having that real time gives us a real benefit in that regard.
Okay, cool. All right, well, listen, why don't we go around the table here and just get some last thoughts from everyone here. So Nick, why don't you start off? You had the last comment there, and give us your last thoughts, and then we'll go to Bronwyn, Ken, and then I'll wrap it up.
Yeah, look, I just wanted to say it's been a pleasure working with you guys on this project, and it's fantastic to see the ways in which you're using the data sets. And yeah, looking forward to continuing to work with your team. So thanks very much.
Great. Bronwyn?
Yeah, I share the same sentiments as Nick. So this data set is one of the best, and I probably shouldn't say my favorite to work on. But you know, when we're dealing with a project that has great geologists and people that are really capable to push the data to its limits is really valuable for Fleet. And we appreciate the time Power Nickel has spent with us. And yeah, we're really looking forward to next year's work and also seeing the drilling results over the winter.
Super. All right, Mr. Kenneth?
Well, same here. I was, I guess my conclusion will be maybe I was a little reluctant in believing in the technology at first, as you did mention, but hey, did it worth the try? Absolutely. I mean, as it's been documented, it's a complementary data set that, you know, we could have lived without it, but it makes our life so much easier in terms of being capable of interpreting what's happening at depth. That, yeah, very, very, very successful story on my end, the way I've used the data for sure. So.
Yeah, so you know, when I look at it from the business perspective, I you know, because part of a junior mining company's mission life is obviously you got a geological vision of what you've got, and then you've got the reality of what you got, and then you need to bring that to the market. So we had this vision of NISC and now we've gotten a pile of very positive results, and then it's like how big can it be? Is sort of the next key question. We think we've established it's going to be a commercial deposit. We think that's why people like CVMR are involved and are working towards a feasibility study. So we believe we can get this thing operational, in 4 or 5 years, at some scale. The question is, well, how big? And eventually, this thing could be, really a monster. And that's why we look at like and 1, 2, 3, 4 as like enormous opportunities for us as explorers to test what looks at this point to be a really great exploration bets that have got all the right signatures, the right sort of characteristics that we would think would be attractive and receptive to a successful drilling program. Now, will they be successful? That's that's ultimately what we'll find. But we'll, even as I suggested, even from not being successful, we'll learn how to be more successful. But I know one thing: in the history of time, every single nickel sulfide mine in the history of the world was multiple pod. So is it possible that NISC will only be a single pod discovery? Well, I guess anything's possible, but based upon what we're seeing from the data and everything else, I believe we're onto a multiple pod discovery here, and this could be really an amazing nickel discovery story. So we're going to look forward to bringing you more conversations like this over the year with Fleet, and ultimately soon with CVMR. As we explore the other side of the story about the production. But we're pretty stoked about what's happening at Power Nickel, and we look forward to bringing it to those people that are interested in our story and in our stock. And we'll look forward to keeping you engaged over the coming year. And we wish you all a happy holiday season. I hope you have a really great one. It's been a bit of a rough year for humanity this year, and we could all use a little peace and goodwill. So God bless you all, and have a great night. And thanks for attending our show today. Cheers.
Thanks, Paul.